Hello and welcome to the 7th chapter and also lecture number 35, where we will begin a new chapter called Approximation Method. So first we are going to take a look that why at the first place we require an approximation method. So let me first tell you that for hydrogen atom we have solved exactly a Schrodinger equation, and we have found out well-defined solutions which can satisfy all the conditions of hydrogen atom, and it can satisfactorily explain all the properties including the orbitals and energies etc. in hydrogen atom. But hydrogen atom was a one electron system. So what happens if we just move on to a two electron system, helium atom? So helium is the simplest of multi-electronic atom, and although remember helium atom is not of much interest to the chemist because it's chemical inertness. Anyway, so let's take a look at it, that how easy to solve the energy of the helium atom and the wave functions. So since there are two electrons, and so if we designate the proton here and electron 1 here and electron 2 here, so it becomes basically a three-body problem. Okay, so where there are three individual coordinates. So remember, for hydrogen atom, we incurred the model of a diatomic rigid rotor. Why? Because for hydrogen atom, forget about this. This is a two-body problem. And since the mass of the proton is much higher than the mass of electron, so we can think about a reduced mass and we can fix the position of the proton. You know, it seems logical that the proton doesn't move since because of its very heavy mass. Then the electron may move around and we have a diatomic rigid rotor. You know, it is equivalent to a diatomic rigid rotor. But here, now we have a three-body problem. So with our best possible approximation, we can assume that the mass of the proton is once again is much higher than the two electrons. In the same way, we can fix the position of the proton here, and then we can have a two electron system. So if we fix the position of the proton, then we can try to write a Schrodinger equation out of this. So Hi is equal to E psi, and then we can write the kinetic energy of the electron 1 using the Laplacian expression or operator, for electron 2 using the Laplacian operator. So this is the Hamiltonian operator is now consists of the kinetic energy part plus the potential energy part. Now the potential energy is the energy just comes out of the electrostatic attraction between nucleus and the electron. So the expression goes something like this. Okay, so this is a purely Coulombic interaction. But still there is another part that we cannot ignore, that is the inter-electronic repulsion. That means how these two electrons would electrostatically repel each other. So therefore we have the repulsion term here. So now the entire first part can be split into the two individual Hamiltonian operator for electron 1 and electron 2 plus a term which stands for the inter-electronic repulsion. Now, had that been not in place, so the situation would have been so simple. So we can easily split the Hamiltonian into the summation of the two individual Hamiltonian for the two electrons, and therefore, in that case, psi would have been a product of psi 1 and psi 2. This comes from a theorem that we are already familiar of. But unfortunately, this is not the case though. But here the problem is how to know what is the distance between the two electrons. Okay, so in fact it is very difficult to know, or rather it is impossible to ascertain the value of it, and due to this the Schrodinger equation for the helium atom cannot be solved exactly. And as a matter of fact, hydrogen atom is the only system where the Schrodinger equation can be solved exactly, and from helium atom onwards it is not possible to solve the Schrodinger equation in exact fashion. So the question is, what now? what is the way out? So does quantum mechanics give us a way to predict the energies of helium and other atoms, other multi-electronic atoms? The answer is yes, and we have to use some approximation. So that means we can predict the energies as accurate as up to 99 point some percentage. So which is good enough to be real, or good enough to be accurate as it is expected to be solved by a Schrodinger equation. So therefore, this chapter deals with approximation method. That means the method that will teach us how to predict the energy of some systems where we cannot find a direct solution from Schrodinger equation, and it teaches us how close we can get to the most expected real value. Okay, and there are two methods for approximation method. So one method is called the perturbation theory, which I am going to start next, and another method is called the variational theorem or the variational approach. Okay, so this in this lecture number 35, we will start with the first method. It is called the perturbation method, or rather the perturbation theory. Okay, so let's screen the board and we'll start with the perturbation theory. So we first start with the definition of perturbation theory. So it is defined as the method of expressing the solution of one problem in terms of another already solved problem. So what's that? So let me explain it in simpler words. So harmonic oscillator, diatomic rigid rotor, hydrogen atom, etc. These are the systems, or in fact particle in 1D box, or free particle confined in a 1D box. Those are the systems that you are already very familiar of, and you know that for these the Schrodinger equation can be solved exactly, and we can write the corresponding wave functions as well as the energy terms. But on the contrary, we have just now seen that Schrodinger equation for helium atom cannot be solved exactly. The same thing goes with the anharmonic oscillator, where in both these cases the Schrodinger equation cannot be solved exactly. So what's the utility of the perturbation theory? So the perturbation theory says that we can take an approach where we can solve the problem of helium atom by taking the help of hydrogen atom itself. So that means what? So that means we can think about that the helium atom is probably, this is the best way to represent that the case of helium atom is probably, it is basically the case of hydrogen atom plus some change, so that the entire hydrogen atom plus some change would resemble helium atom, and that change is called perturbation. Okay, so the word perturbation means change. And also the same way, if I want to know the energy of an harmonic oscillator, okay, so we will follow the same approach over here. That is, we will think that as if it resembles something which is the summation of basically the harmonic oscillator plus some change, and the some change is the perturbation. Okay, so what happens here, that whenever we write the Hamiltonian operator for the unknown term, so let's write the Hamiltonian operator, which is for the entire system. So we write the system should be now equal to some already known Hamiltonian, so I call it H naught. So H naught stands for the already solved standard system. For helium atom, it is hydrogen atom. For anharmonic oscillator, it is the Hamiltonian for the harmonic oscillator. Plus some perturbation, and we denote this thing as H1. So remember, there are more than one, or in fact there can be infinite number of perturbation terms, say H1, H2, H3, H4, and those terms 1, 2, 3, 4, 5, 6 has a name. So the term 0 here, it stands for the zero order perturbation, means the no perturbation as such. So the system can be solved directly. And then we have H1. The 1 stands for the first order perturbation. Now if I introduce another term 2, it goes as the second order perturbation, third order, fourth order, and so on, and it can go infinitely as long as we can think that putting some more higher order terms would make the system take the system energetically closest to the unknown system. Okay, but for the sake of our syllabus here in this quantum chemistry CY4301, we are going to confine our discussion only up to the first order perturbation. So we are going to make our system simple. So we will only confine up to H1. So therefore, this H naught, okay, or H0, whatever, this is called the unperturbed system. Okay, this is called the unperturbed term. Okay, and this part is called perturbation term. Okay, and in our case, this is the first order perturbation. Okay, so we can approach whatever I have said in a simplest manner with two simple examples. Okay, so that means we are going to write the equations for hydrogen atom and harmonic oscillator to show you that how using this perturbation approach we can expect to write a Hamiltonian for the helium atom and anharmonic oscillator, or the systems those we cannot solve exactly by Schrodinger equation. Okay, so let's quickly clean the board and show you by two very simple examples. Okay, so let's do that. So here I have just rewritten the Hamiltonian operator for the helium atom and also the Hamiltonian operator for anharmonic oscillator. Now you see the potential energy term for anharmonic oscillator comes from a Taylor expansion series, and it takes up the form like this with further higher order terms like x to the power 5, x to the power 6, so on. So therefore the Hamiltonian operator becomes the kinetic energy operator plus the potential energy operator. So all those terms now appear as the potential energy. So therefore, if you take a look at both the Hamiltonian for helium atom and anharmonic oscillator, so then you can probably recognize that part of this is actually your H naught, which is the unperturbed Hamiltonian. Okay, and another part of this Hamiltonian, means the unknown Hamiltonian, is basically this one, and that is the perturbation term. So therefore, for helium atom, this part becomes your first order perturbation, or H1. So similarly for anharmonic oscillator, we can easily recognize that it originates from a known system, which is it contains an unperturbed Hamiltonian H naught plus, then these are the terms, so we can call it the H1 plus H2. So this is the first order perturbation, and this is the second order perturbation. So as we mentioned that we are not going to consider a perturbation higher than first order, so we can neglect it. And therefore we can tell that here this term is the first order perturbation for an harmonic oscillator, and here this term is the first order perturbation for helium atom. Now if in this case if gamma is equal to B is equal to 0, then what would happen? That an harmonic oscillator starts to behave as harmonic oscillator. So this is the approach for the perturbation theory. So therefore the Hamiltonian goes like this: H naught plus H1, and remember this H naught forms the eigenvalue equation with respect to psi naught. So therefore we can write that this is the energy of the unperturbed system, or this is the unperturbed, the original energy. That means if we can solve this, we get E naught, which is the energy here for the combination of two electrons, hydrogen atom. That means if we think about that, so there is no interelectronic repulsion. So in that case, if the energy would be equal to the summation of two individual hydrogen atom, and then here also this unperturbed term would give E naught, would give the energy of the harmonic oscillator. Okay, and what else? So therefore, now our original intention is to find E. Okay, so we need to find E. Okay, why E? Because the corresponding energy for this Hamiltonian would be E. But the problem is we cannot find an eigenvalue equation corresponding to H. So we cannot write H is equal to E psi. It's not that simple. So we have to find E separately. And also the corresponding solution for E is actually psi. Alright. So we also need to find psi. The question is that then how we can define E and psi. So therefore here we can define that the unknown psi that we are going to solve is also stems from the same perturbation theory. So that means it is the summation of psi naught, means the original solution plus some changes. So we can write that probably this unknown psi is psi naught plus delta psi. So delta psi is my unknown term. And then also the total energy E that we are going to solve, basically this is also E naught plus some change, that is delta E. So therefore the approach says that if we want to find the unknown energy for the new system, which we cannot solve directly, if we try to find delta E, then definitely from E naught, if we add that to the E naught, we will find our desired energy value for that unknown energy system. Okay, so our goal is to find out delta E. So the question is how we can find delta E. So of course we have to take a little bit of we have to take the help of mathematics to find out quantum mechanical or mathematical expression for delta E. Okay, so that's what we are going to do next. We want to derive an expression for delta E. Okay, so let's start it over here. So here we are in a process of finding delta E. So let's start with the assumption that psi be the unknown solution. Okay, where psi is equal to psi naught plus delta psi. And if we are successfully, if we become successful to find psi, then of course there is no problem to write that in that situation H psi is equal to E psi. Because we are assuming that the unknown solution psi there exists, and that forms an eigenvalue equation with this. Okay, but earlier I said that assuming psi, we cannot write or we cannot solve it directly from such kind of equation, because this H is basically unknown. So from this we cannot directly solve psi, but we are assuming that there exists a perfect psi which satisfies an eigenvalue equation, which is this. So here of course E is the unknown energy, and it is the summation of unknown energy plus some perturbation delta E. And of course the Hamiltonian is summation of a known Hamiltonian plus the first order perturbation, because we are only dealing up to the first order. And now here the most important assumption that we are going to apply, that this perturbation term is actually very small compared to the original unperturbed Hamiltonian. Okay, so that means H1 is very small with respect to H0. Okay, and of course it's needless to say that H0 psi naught is equal to E0 psi naught, and this is an existing eigenvalue equation we can write and we can directly solve. Okay, because H0 is totally known. Okay, so hopefully there is no confusion up to this point. So let's start. So given H psi is equal to E psi, okay, and from that we are expecting it at the end. So then if it is true, then of course we can write that we can expand H0, so or we can expand H0 as the H cap as H0 plus H1 cap multiplied by, we can expand the psi term, that is psi naught plus delta psi, okay, is equal to E psi. Good. And then of course we can break this term, so or we can write H0 psi naught plus H0 delta psi plus H1 psi naught plus H1 delta psi, okay, is equal to, we can write so here of course we have to expand the psi, so that means psi naught plus delta psi, okay, so we get E psi naught plus E delta psi, okay. So now here we see we have so many terms on the left hand side and only two terms on the right hand side. So first let us see that we already have H0 psi naught is equal to E0 psi naught. So here H0 psi naught, and on the right hand side, okay, on the right hand side, okay, so what I think we need to do is that we still need to expand the E term. Okay, so what we can do, actually we can break this equation into one more way. So is equal to E naught plus delta E, okay, multiplied by psi naught plus delta psi, of course. And then or I'm going to write one more step here, H0 psi naught plus H0 delta psi plus H1 psi naught plus H1 delta psi is equal to, we have E naught psi naught plus E naught delta psi plus delta E psi naught plus delta E delta psi. Okay, so here we have of course four terms on the left hand side and four terms on the right hand side. So now let's see, here we already have H naught psi naught is going to be E naught psi naught. So now we can find those two terms here. So since those two are equal on both sides, so we can now cancel it out. Now another thing is here that also we have a delta E delta psi term. So I already told you that since these first order perturbation, okay, or the perturbation term is a very small term compared to H0, then here we have a product of delta E. So similarly delta E should also be very small and delta psi would also be very small. So this is the product of the two very small terms. So we can neglect. So what else? Here also you see H1, which is a very small term, and also delta psi, again a very small term. So the product of two small terms, and we can cancel it out. Okay? So if we cancel it out, so what we have is something like this: H naught delta psi plus H1 psi naught is equal to E naught delta psi plus delta E psi naught. Okay? So if we look at this equation carefully, you see each of these terms here is a product of a big term and a small term, a small term and a big term, a big term and a small term, a small term and a big term. So wherever we have such product of a big term and a small term, definitely we cannot neglect it, number one. And number two, each of these terms has a name, and it is called that first order correction. Okay, so these are called the first order correction, and the second order corrections is a product of two small terms, and therefore we have already neglected. So this is another reason that why we are confining our discussion up to the first order term, because the second order and onwards the terms becomes even smaller. Okay, so for any significance we are only considering up to the first order term. So alright, so here we have now, we have got something over here. So what to do next? You tell me. What was our goal, purpose? I have written it here. Our goal was to find delta E. So what we are going to do here? So we are going to find out delta E. So out of these four terms, you pick the term that contains delta E. Here, this is the term that contains delta E. So therefore, it's better if we keep that term in one side and everything else in the other side, and let's see what happens. Okay, so or we are going to transfer this part over here, and so that delta E terms get to the right side. So what we can do here, so let's erase the board and let's start it from the top, because we are going to do some more derivation step. Okay, so let's do it here. Okay, so I have rewritten this equation here by taking this term from the right side. So now you see that we have delta psi part common in two terms. So what we can do is we can take H naught minus P naught common from delta psi plus H1 psi naught is equal to delta E psi naught. Okay, so we have got this equation. Now, still what? Once again, we need to find delta E. And here on the right hand side, we have delta E multiplied by psi naught. The question is, from this, can you vanish psi naught so that you have only delta E term is there? You can tell, of course, we can divide both sides by psi naught, so that right side we have delta E, and left side we have this thing is equal to plus H1, and here we have something divided by psi naught. Okay, but would that solve our problem? So let's think rather in the terms of quantum mechanics and quantum mechanical theorem. Which is the other way of vanishing psi naught here only by keeping delta E. So think about this. Okay? Yes, we can do that with an assumption that, let's assume, and of course we don't have to assume, we have to start with this, that psi naught is normalized. Okay? So now you can quickly understand the hint that I wanted to give you. And of course what we're going to do that we are going to multiply both sides by the complex conjugate of psi naught, that is psi naught star. So if we do that, and not only that, we multiply both sides by psi naught star and integrate with respect to the volume element, which is d tau. So if we do that, what we're going to get is integration psi naught star h naught minus e naught delta psi, and then plus integration psi naught star h1 psi naught d tau, okay, and then is equal to integration psi naught star delta e psi naught d tau. Okay. So now let's take a look. What are the terms that we get from this equation? So, or what I'm going to get is this term, that is psi naught star h naught minus e naught delta psi. Of course, we have this delta tau term I missed earlier, delta tau, plus this term. So does it vanish? No, it does not vanish, because we have h1 operating on psi naught, and we don't have an eigenvalue equation, so that we can have something e1 psi naught, so that the psi naught star psi naught delta tau integration becomes 1. So we cannot vanish that. So therefore we have to keep that term, unfortunately. Psi naught star h1 psi naught delta tau. But what about the right hand side? The right hand side, delta E is just a multiplication operation. So delta E is not an operator. So we can easily take delta E out, and then a normalized function psi naught star psi naught delta tau is 1. So therefore, on the right hand side, we have simply delta E. So now you see we are approaching somewhat discernible. So now delta E is equal to this term plus something else. Okay. So now let's take a closer look about what about this psi naught star, this term. Can we change it to something else? So you once again, let's take the help of the theorems of quantum mechanics. So you see that we have this equation already. So h naught psi naught is equal to e naught psi naught. So of course, if we can take this equation, this part in the left hand side, or we can simply write h naught minus e naught, okay, whole multiplied by psi naught is equal to 0. Okay. So somehow, if we could write that this part multiplied by psi naught here within this integration, then we can vanish this integration. But this is not the case though, because this is something else. Psi naught star h naught minus e naught this is getting operated on delta psi and then d tau. So how we can replace delta psi with psi naught? But look at the left hand side, we have psi naught star. So does that expression remind you of something? Yes, chapter number 4, you recollect the condition of, okay. So condition of what? Do you still remember? Okay, so means it's a property of operator. So what is the property of operator that makes sure that the corresponding eigenvalues are real? Okay, do you remember? Okay, so I believe that you have remembered that this is called the condition of Hermitian operator. So now we are going to apply the condition of Hermitian. Okay, or we are going to apply the Hermitian condition, or if we apply the Hermitian condition, because this is only H naught, and H naught is the Hamiltonian operator. It must be linear as well as Hermitian. So if we apply the property of the Hermitian operator, then we have delta psi. Okay, all right. So it becomes delta psi. It comes to the left hand side. All right, and now we have H naught minus E naught. Okay, star on psi naught star. Okay, delta tau plus this psi naught star H1 psi naught delta tau is equal to del E. Alright, so that we can write following the Hermitian condition, or rather delta E, and since this is a real operator, so we can also write it like this. So as if this operation is being dealt on this psi naught and everything star conjugate, okay, the complex conjugate. Okay, so we can write that. You can now recognize. So things are taking place something like this is equal to delta E. So now therefore, you see, applying the Hermitian condition from here to here. So if you have forgot about it, you can quickly take a look, and you see that the condition, if we apply, so delta psi goes here, and this part gets operated on the psi naught star. Okay, so we have already this part is equal to 0, so this part then vanishes. If this vanishes, okay, then we have the final value of delta E is equal to something like this. Psi naught star H1 psi naught delta whole integration is equal to delta E. So we can simply write the outcome once again in a clearer fashion, that the unknown energy perturbation delta E becomes integration psi naught star H1 psi naught delta tau. Okay, so if we manage to find out this, we can find delta E, and from delta E we can find E. E is equal to E naught plus delta E. We can simply add to the E naught. So the thing is, the psi naught is from the known solution, so we can simply take psi naught, and we can have to take the complex conjugate of psi naught. Fine. So it operates like this. The H1, that is the first order Hamiltonian perturbation, getting operated on psi naught, and which is multiplied with the complex conjugate of psi naught, and whole integration with respect to d tau. Okay, so since we have found out this expression for delta E, now we are going to take two simple examples to find out that how this exact delta E term is applied. Okay, so before we go, we must also appreciate one more thing, and that is still we have the psi part. Okay, so psi is equal to psi naught plus delta psi. So the question is how to find psi. Okay, because the problem is here, using this, although you can find delta E, but you cannot find psi from directly solving the Schrodinger equation, means H psi is equal to E psi, although you can frame it, but you cannot solve it from there. Means had there been a psi known, you can write H psi is equal to E psi, but the question is how to find psi. So again, in perturbation theory, there are certain approaches, certain method that tells you how to find psi, and it again comes from the Taylor expansion series with some perturbation terms. So, but due to our limitations of our syllabus and curriculum, we are not going into the details of that. So therefore, we from henceforth we will be only interested to find out the perturbation or in simpler manner, the first order perturbation energy correction, that is delta E. And for the time being, we are not concentrating on to find out psi. Okay, so therefore, quickly we take two problems one by one. So the first problem is a perturb system for a free particle in 1D box. Okay, so let's quickly look it and lay out the problem over there. So this is one example that how this perturbation theorem is actually applied. So this is an imaginary system of a perturbed free particle in a 1D box. So what happens in here, the one side of the boundary, okay, the wave function psi actually vanishes here. Okay, right here when x is equal to 0. But here, now the problem is what happens, that whenever the particle approaches A, ideally at here, in between this 0 to A, the potential energy is 0. But here, right at the boundary wall, there is some finite potential energy. So that means as if that the limit has been slanted a little bit. Okay, so we call this a problem of a slanted bottom. So that means at one end it has the energy En naught. Okay, N stands for the quantum number, so these are the levels 1, 2, 3. And here at the another end, there's the other end of the wall, there is some energy greater than En naught. So we call that the delta E. Okay, so you have to find out the delta E. All right, and if it is so, then we can graphically represent that at least the energy levels are somewhat slanted. Okay, because of that additional potential energy. So that means whenever so that side the particle is completely free, and on the other side the particle is under some kind of binding force. Okay, so particle is in a force field, so particle is not completely free, that means the particle is partially free. So this is a hypothetical system. It's very difficult to relate it to a real life problem. So anyway, let's come back to that. So what is our expression for delta E? So as we know, the delta E becomes psi 0 star H1 psi naught delta tau. So here the H1 term is given, it is known, it is V over A multiplied by X. Okay, and this is our psi naught from our known solution. Okay, so we can simply write this down. Okay, and so psi naught is equal to this psi naught, so we have to take the complex conjugate, means basically the same thing, and then H1 is V over Ax, and if we try to solve this, okay, then we will find that the delta E actually comes out to be V over 2. So therefore the energy, okay, that is E0 naught plus delta E is equal to the energy term for the free particle in a 1D box plus V by 2 plus some other terms which we can neglect at this time point. So you see, this is much simpler approach to find delta E. So we can directly use this expression and find the value of delta E. And of course this is a finite value. So we can quickly talk about another example of anharmonic oscillator. So let's quickly clean it and let's pose the problem over there. Okay, so here comes the case of the Harmonic Oscillator, and perhaps it is the simplest of all problems that are classically known where the perturbation theory is applied. So we are only considering up to the first order term for the potential energy expression for anharmonic oscillator. So we are neglecting the other terms. So we have up to 1 over 6 gamma x cube. So we are going to find out delta E. So once again, what is the expression? The expression goes psi 0 star and of course H1 psi 0 delta. So what's our H1? So H1 is basically this term, that is 1 over 6 gamma x cube. So therefore we have to write the integration. So of course I forgot to write the limits of the integration in the free particle in a box. It should have been 0 to a. So here of course instead of del tau, since this is a one-dimensional oscillator, we have to take dx. So probably if I have written it d tau in the last example, so please correct it with dx because it was a one-dimensional case. And of course the limit is from minus infinity to plus infinity. So that becomes minus infinity to plus infinity, and we have instead of h1, so 1 over 6 gamma part comes out, so we have psi 0 star x multiplied by psi 0 dx. Okay, so here we can talk about psi 0 n because it is dependent on n, the quantum number for anharmonic oscillator. So now you see that psi 0, okay, psi 0 n, it comes from a Hermite polynomial, okay. So its expression can be solved from Hermite polynomials, and we see that for n is equal to even or odd, this psi 0 n can be even or odd. So whatever it is, either n is equal to even or odd, you see this whole function due to x in nature. Or if we talk about the ground state, that is n is equal to 0, and then this would be, it would become an x cube type of function. So anyway, the summary is this would be an odd function. Okay. So as we know, on the minus infinity to plus infinity integration odd function dx would become is equal to 0. So that means what? So that means the delta E part for first order perturbation for an anharmonic oscillator is 0. Of course, it can be non-zero if we move to the other term, which consists of x to the power 4. But since the term is very small, so we can neglect it for the time being. So this is the essential summary of the perturbation theory, and this is how it is applied. So we have found out what is the expression for or how to find out delta E. So we find it out by evaluating this integral, and I've also figured out how to, or the basis of derivation of such kind of integration. Okay, so I think with this is enough knowledge on the perturbation method. So we end it here, and we will take up some more specific problems later. So for next lecture onwards, we will concentrate on the variational theorem, our next and the last approximation method. So please study it, and I will see you in next lecture. So till then, goodbye.